something strange started whispering from the edge of our solar system. At first, it was barely noticeable, weak signals buried under static. They didn't sound like a message. Not by any normal definition. It was garbled data from an old spacecraft, Voyager 1. A machine that's been drifting in deep space for nearly 50 years, now sitting more than 14 billion miles away. For months, it sent back nothing but digital gibberish. Everyone assumed it was a glitch. Random nonsense. Until patterns appeared. Subtle. Repeating. Something that suggested maybe we weren't listening the right way all along. Engineers scrambled to make sense of the data. Their tools, designed to decode clear binary telemetry, kept failing. But something deeper began to trouble them. What if the real mystery wasn't in space, but in how we've built the tools to understand it? Voyager's distorted signal wasn't telling us a technical story. It was challenging us to rethink our perception. To ask if what we call noise might actually be something more. Something trying to communicate, but in a way we've never thought to interpret. Noise, it turns out, might speak its own language. In November 2023, NASA's Deep Space Network began receiving those strange reports. Voyager 1, humanity's most distant machine, was still sending signals. But the data was garbled beyond recognition. Just static-filled, messy strings of characters. It looked like classic hardware decay. And that made sense. This was a spacecraft launched in 1977 after all. But what didn't make sense was the consistency. The data wasn't just random. It had rhythm. Patterns that shouldn't exist if it were just failing memory or broken systems. NASA's decoding software couldn't make heads or tails of it. These tools were built to handle structured telemetry, complete with error correction and predictable patterns. But none of that worked here. Engineers tested every known failure mode. Flipped bits, corrupted memory banks, fried circuits. Nothing explained it. They even compared the signal to old spacecraft errors from the past. Still nothing. And yet Voyager 1 kept operating. Its systems weren't shut down. It was sending data consistently, just in a form no one understood. In an attempt to fix it, a JPL team tried redirecting memory usage on Voyager. It was a long shot, but it partially worked. Some readable telemetry came back. But not from the past, it only worked moving forward. The weird signals from earlier remained untouched. Still corrupted. Still full of mystery. That made some researchers pause. What if the issue wasn't a glitch at all? What if the bad chip in the flight data system was doing exactly what it was supposed to, but in a way we couldn't grasp? Some scientists quietly flagged that these patterns began right when Voyager crossed another deep threshold into interstellar space. Officially, the problem was called a glitch, solved by memory rerouting. But off the record, archived data logs were marked for further study. What made this case different wasn't just the corrupted data, it was how the scientific community responded. For once, engineers started asking questions that weren't purely technical. Could this really be just hardware failure, or something more? For decades, spacecraft problems were handled the same way: identify the error, fix or work around it, and move on. But this time, something was different. The glitch didn't act like a glitch. It had structure, consistency. It repeated. And that persistence opened the door to speculation. Could this be an unknown failure state? Or had Voyager stumbled into something unexpected? Something possibly bigger? Voyager 1 once again had become a messenger, not just across space but across disciplines. Engineers, theorists, mathematicians, all suddenly interested. Once NASA confirmed Voyager 1 was still alive and transmitting, the priority became decoding its message. Its communication protocols relied on rock-solid systems, Reed-Solomon and convolutional coding. These had worked flawlessly for decades, even through solar storms and deep space noise. But this new anomaly broke the pattern. The tainted packets passed the basic checks but still didn't make sense. It wasn't like they were broken. They were intact, but they meant nothing. This baffled everyone. NASA's decoding tools rely on known formats, specific headers, sensor readings, system stats. But these new packets didn't match anything. They weren't showing system temperatures, voltages, or orientation data. They didn't resemble any known format. Worse, the patterns didn't even look like typical faults, like flipped bits or misaligned packets. NASA's team tried running the data through all old filters, trying every trick in the book. Nothing worked. The signal remained stubbornly strange. Faced with this wall, some engineers at JPL began thinking outside the box. Quietly, without official approval, they started using experimental tools. A few pulled in AI-based pattern recognition systems, machines trained to find meaning in chaos. Others built simulations trying to replicate the corrupted data by introducing different failure types. No method gave a full answer, but strange things began to emerge. Mathematical structures. Subtle repeats. Just enough to keep the curiosity alive. What made this situation so unique wasn't just that they couldn't solve it, it was how stable the problem was. This anomaly repeated itself across different ground stations. Across different decoding centers. It wasn't Earth-based interference. It wasn't a local error. It was coming from Voyager itself. And that opened the floodgates for new theories. Some engineers blamed firmware. Signal experts suspected modulation issues. And others, well, they began wondering if the machine was generating complex output unintentionally. In most technical fields, ambiguity is a problem. But here, ambiguity became the clue. Something was clearly happening. Just not in any way they were prepared for. That's when new voices entered the conversation. People outside the traditional space engineering circles. Theories expanded. Tools changed. Voyager 1's odd data began to feel less like a broken transmission, and more like a puzzle meant to be unraveled with a new kind of thinking. With classic tools coming up short, some researchers turned toward cutting-edge options. They asked, could this be a job for quantum computing? NASA wasn't officially using quantum processors for deep space data. But some university labs in Europe and Canada were already experimenting with using quantum algorithms for pattern recognition in space signals. These systems don't process data the way classical computers do. They explore all possibilities simultaneously, using entanglement and superposition. One such team, working in the Netherlands, got access to archived Voyager data through a collaboration with ESA. They had a prototype quantum computer ready, built for analyzing astronomical noise. When they ran the data, something weird happened. The random noise started forming faint geometric shapes. Patterns. Recurring and symmetrical. Not the kind you'd expect from hardware failure. These shapes were too clean. Too structured. Suggesting design rather than chaos. The team didn't jump to conclusions. They were careful. They didn't claim proof of anything. But the fact that these shapes kept showing up across different runs, across different algorithmic setups, was hard to ignore. These weren't one-off flukes. The quantum processors saw things that classical systems couldn't. Interference patterns revealed sequences. Mathematical structures that looked intentional. At the very least, they showed that the noise wasn't entirely random after all. As rumors of these findings reached NASA, more engineers began requesting similar tests from academic partners. Voyager's systems were never built for this kind of complexity. But now there was a growing belief that this might not be a glitch at all. Maybe it was something buried in the data, only visible through quantum eyes. A side project had suddenly become a research priority. The focus had shifted. The question wasn't, how do we fix this? Anymore, it was, what are we actually looking at? As the quantum algorithms kept digging, some of the patterns they uncovered started to raise eyebrows. Mathematicians and data analysts working alongside the quantum teams began spotting something specific. Prime numbers. Sequences embedded in the noise that seemed to follow prime distribution. That's a big deal. Prime numbers are fundamental to mathematics, encryption, and pattern design. They're rarely random. Their presence in a corrupted space signal? That was worth looking into. What was remarkable wasn't only the occurrence of primes, but their sequential appearance, with consistent intervals in the midst of the larger data stream. This level of organization was hard to account for by system noise or hardware malfunctions alone. The patterning of these primes within such an extended and complex data stream seemed almost deliberate, suggesting there might be something more at play. Beyond the initial appearances of prime numbers, some visualizations of the data, when processed and represented spatially using quantum Fourier transforms, revealed even more intriguing results. The data revealed dramatic spiral-structured patterns that seemed to emerge from the raw telemetry. These patterns weren't random or chaotic. They strongly resembled familiar geometric shapes like the logarithmic spiral, a shape seen in everything from galaxies to the growth patterns of plants and seashells. The more complex the data became, the clearer it was that the structures carried a distinct mathematical order. Something that could not be easily explained by simple computational errors or interference from nearby cosmic radiation. As scientists refined their models to interpret the data, the realization set in that they might be looking at something far more profound than a mere technical anomaly. To a few researchers, the symmetry and complexity of the shapes strongly suggested a higher degree of intentionality. These weren't simply abstract or meaningless math outputs. They were visual records that came directly from raw spacecraft data. This data had been processed using next-generation quantum analysis methods, which were much more advanced than the methods initially employed in the 1970s when Voyager first sent its golden record. The spirals, the mathematical sequences, the intervals, these were features that did not resemble normal signal noise. These were structured outputs seemingly designed. Although most of the scientific community remained cautious about jumping to conclusions, the fact that these prime-based intervals and spiral symmetries appeared so clearly within the telemetry made it impossible to simply dismiss them. There was something there. Something that might be outside the realm of what was previously considered ordinary. Throughout history, prime numbers and geometric shapes have often been theorized as potential universal signals that could transcend the boundaries of culture, language, and biology. In the search for extraterrestrial intelligence, these are considered among the most promising signs of intelligent life because they represent knowledge of mathematics that would be universally understood, even by species far beyond Earth. The fact that these prime intervals and spiral patterns appeared in data previously dismissed as mere corrupted telemetry reopened the age-old question of whether we are alone in the universe or if we are perhaps receiving silent communications from an advanced intelligence. While no one was eager to announce any concrete conclusions, the fact that these signals were so carefully structured, and so unlike anything else the spacecraft had ever encountered, raised a much larger possibility. What if Voyager's signal anomaly was not a malfunction at all, but a message, or at least, part of a communication network that we didn't yet fully understand? Yet, despite the excitement generated within certain research communities, no one immediately rushed to proclaim that Voyager 1 had inadvertently become a participant in a communication exchange with an extraterrestrial civilization. Skepticism was high, and many took a more measured approach. But the discovery of mathematically sophisticated patterns where only noise was expected rekindled the flame of interest in the search for extraterrestrial intelligence. The anomaly in Voyager's signal didn't just indicate a malfunction or glitch. It suggested something far more complex and purposeful, perhaps even beyond our current technological capabilities. One of the most astonishing developments during the continuing study of the Voyager 1 anomaly was the discovery of a particular pattern in the decoded signal that closely resembled the very pictures and information contained within the Golden Record. The Golden Record, a message carefully designed by NASA in 1977, was a disk sent with Voyager 1 and 2 containing an array of sounds, images, and messages meant for potential extraterrestrial life. It included mathematical sequences, natural sounds, music, greetings in multiple languages, and images of Earth. The fact that part of the anomaly in Voyager 1's signal seemed to mirror the structure of these visual elements was nothing short of remarkable. It wasn't an exact match, there were some distortions and some portions of the data appeared corrupted or incomplete, but certain aspects of the decoded patterns showed structural similarities to the diagrams and images carried on the Golden Record, such as the famous diagram of the hydrogen atom and the map of the solar system. These alignments, while not perfect, were certainly striking. It was almost as though the signal was echoing or responding to the message Earth had sent over 40 years ago. This discovery quickly became a source of intense debate. Some scientists believed that it was nothing more than an example of pareidolia, the psychological phenomenon where people see patterns in random data. According to this view, the brain is wired to recognize familiar shapes and forms, even in the most chaotic data sets, and thus, it was simply a coincidence that these patterns resembled the images on the Golden Record. Yet, for many others, this coincidence was too perfect to be dismissed outright. It raised an intriguing possibility. Could the anomaly be a sign that the Golden Record, or at least the information it contained, had been received by some external intelligence? If so, might that intelligence have been trying to communicate or respond to Earth, using the same format as the original message? While the idea of a response to the Golden Record might seem fantastical, the implications were profound. If this were true, it would mean that Voyager 1, a spacecraft originally launched with the purpose of broadcasting humanity's existence to the stars, had become the unlikely conduit for a form of interstellar communication. The idea that Voyager 1 might not just be a one-way emissary, but a participant in an ongoing exchange with extraterrestrial intelligence, opened up a new avenue of exploration. Scientists speculated. What if this was the beginning of a communication network that spanned across the cosmos, waiting to be discovered? What if this was just the first subtle hint of a conversation that had been quietly unfolding in the vast emptiness of space for decades? Even so, while the debate raged on, no formal publication confirmed that the patterns were anything but a technical anomaly. The scientific community continued to emphasize caution, and the possibility that these patterns could represent an intentional communication remained speculative at best. But the discovery itself was undeniable. It was a hint, a glimpse into something larger, perhaps a message that had been encoded within the signal for over 40 years, waiting for the right tools and knowledge to uncover it. As the investigation into Voyager 1's anomalous signal progressed, three primary theories began to take shape, each offering a different explanation for the phenomenon. The first and most conservative theory was that the unusual patterns were simply the result of a rare and highly unlikely hardware glitch. Voyager 1 had long since outlived its expected lifespan, and its systems were aging rapidly. This theory suggested that the signals were the result of a malfunction or error in the spacecraft's instruments, which were struggling to keep up with the rigors of interstellar space. In this scenario, the regularity of the prime numbers and the spiral patterns would be explained as a bizarre, random artifact produced by the degrading electronics. The second theory, while still speculative, suggested that Voyager 1 was merely a passive receiver, and that the patterns were the result of some external source. According to this theory, the spacecraft's signal might have been reflecting or absorbing signals from an unknown source, perhaps even from an intelligent civilization. The idea that Voyager might have been the unintended recipient of a communication sent by extraterrestrial beings was certainly tantalizing. This theory proposed that the structured patterns in the signal were not the result of the spacecraft's systems malfunctioning, but rather a form of external influence that was interacting with the spacecraft's signals. The third, and most controversial theory, was that the anomaly was the result of direct contact with an extraterrestrial intelligence. According to this theory, Voyager 1 was not just receiving random signals or experiencing a malfunction, but was in fact participating in an interstellar exchange of information. The deliberate structure of the signal, the mathematical precision of the primes, and the resemblance to the Golden Record all pointed to the possibility that the spacecraft had encountered an intelligence beyond our understanding. Each of these theories had its merits and flaws. The glitch theory was the simplest and most grounded in current understanding of spacecraft technology, but it didn't fully explain the complexity and intentionality suggested by the data. The echo theory was an interesting possibility, but it raised more questions about the source of the signal and how such a reflection could occur without any noticeable loss of signal strength or frequency. The theory of direct extraterrestrial contact was the most exciting, but it also seemed the least likely given the current lack of hard evidence. Despite the uncertainty, one thing was clear: Voyager 1's signal anomaly was no ordinary glitch. It represented a breakthrough in our understanding of how we might communicate with other civilizations, and how signals from the farthest reaches of space could hold hidden meanings, waiting to be uncovered by the right set of eyes. Whether it was a malfunction, an echo, or something far more extraordinary, the anomaly represented a mystery that would continue to captivate the imagination of scientists, researchers, and the public for many years to come. Critics claim that until results can be replicated and verified under tight controls, no anomaly, no matter how beautiful, should be deemed evidence for intelligent design. The broader impact of the debate has been both cultural and technical. For many years, searches for extraterrestrial intelligence (SETI) were focused on detecting clear, intentional radio beacons sent directly toward Earth. Voyager 1 has disrupted this paradigm. Instead of offering a response through a broadcast, it suggests the possibility of a reply by modulating our own technology. This change prompts us to reconsider how we understand communication. We are not merely passive recipients of messages. We may already be part of something much larger without even realizing it. Regardless of the anomaly's final explanation, it has led scientists from various fields to ask, what exactly is a message? Who determines its meaning? And in a universe governed by mathematics, does structure alone imply intent? In the aftermath of Voyager 1's data anomaly, NASA has taken a cautious and pragmatic public stance. After engineers identified the problem as a malfunctioning flight data subsystem, they redirected data to a backup memory bank. NASA issued a brief statement declaring the issue resolved, emphasizing that all onboard systems were operating within expected parameters. However, the agency refrained from speculating about the nature of the corrupted data. Particularly, the stored transmissions that still exhibited non-random structure were not commented on in official updates. Behind the scenes, it's reported that NASA was aware of the quantum processing outcomes but chose not to disclose them to avoid premature speculation. This conservative approach contrasts with the increasing interest from international space agencies. The European Space Agency (ESA) has acknowledged the anomaly and reserved emergency research time on its high-sensitivity signal processing arrays to perform an independent analysis. Their director of science cited the unusual structural features within the signal as a reason for further investigation. In China, the CNSA has redirected its deep space listening equipment in Xinjiang to track Voyager's carrier frequency, conducting a full-spectrum analysis. Even Roscosmos, Russia's space agency, known for being more reserved with its telemetry research, has called for international coordination to authenticate the anomaly across multiple observation platforms. The differing responses highlight how various institutions perceive scientific disclosure. NASA, which is deeply embedded in a culture of risk mitigation and public accountability, prefers a cautious approach, validating data before making claims. In contrast, international agencies with more flexibility in their collaborations with experimental computing labs seem more open to exploring anomalies without dismissing them outright. These differing reactions are not just a matter of institutional culture but reflect the changing role of quantum computing in scientific discovery. As independent research continues, there is a growing consensus within international scientific circles. While NASA may have fixed the immediate issue for the spacecraft, the signal anomaly itself remains unresolved. Voyager 1 was never designed to last this long. Launched in 1977 with a mission plan for only 4 years, the spacecraft has now been operational for nearly half a century. It still transmits data from over 15.6 billion miles away, powered by 3 radioisotope thermoelectric generators, RTGs, that continue to provide enough energy for its key instruments and communication system. This extended longevity is a testament not only to the engineering of the 1970s but also to NASA's ongoing efforts in diagnostics, adaptive fault management, and creative solutions developed by teams over several generations. What makes Voyager 1's longevity especially impressive is the harsh environment it now occupies. The spacecraft is far beyond the protective bubble of the Sun's heliosphere, exposed to the interstellar medium, which is full of cosmic rays, radiation, and other unknowns. Despite these challenges, Voyager's onboard systems, including memory banks, command systems, and its digital tape recorder, remain functional, albeit with occasional malfunctions. Its communication system, an old S-band transmitter and low-gain antenna, continues to send coherent signals to Earth's deep space network, using only a tiny fraction of a watt in transmission power. Even more surprising is the extent to which Voyager 1's design has unintentionally opened new avenues for discovery. Its communication redundancy was originally intended to ensure that Earth could always hear from it through multiple channels. But these redundancies, especially in its data encoding and error correction systems, may be why modern quantum processors are able to detect patterns in what was once considered noise. Systems like Reed-Solomon and convolutional coding introduce mathematical structure into data streams, which could serve as a vehicle for more subtle phenomena when subjected to interstellar distortions. In other words, Voyager's longevity isn't just a feat of engineering. It may also facilitate a kind of scientific feedback loop that no one anticipated. The spacecraft is no longer just an artifact of Cold War-era exploration. It has become an ongoing proving ground for the interaction between 20th-century engineering and 21st-century data analysis. Voyager's long life has allowed scientists to revisit its transmissions with technology that wasn't even imagined back when the probe was first launched. With the advent of quantum computers, AI pattern recognition, and high-sensitivity radio arrays, Voyager 1 has ironically become one of the most sophisticated instruments in our scientific toolkit, a bridge between two ages still transmitting across the void. The Voyager 1 anomaly has done more than spark curiosity, it has forced us to reconsider how we look for evidence of intelligence. Traditionally, the search for extraterrestrial intelligence (SETI) has been about looking outward, scanning the cosmos for intentional radio beacons, laser pulses, or other clear signals sent from distant civilizations. But Voyager 1's strange anomaly has turned that approach on its head. What if the signals we're looking for aren't in the sky, but in the machines we've already sent out? The structured, inexplicable patterns found in Voyager's telemetry, whether ultimately of intelligent origin or not, have prompted some researchers to ask, what else might be hidden in our outbound data streams? This new direction is being informally called SETI 2.0, marking a shift from passive listening to active re-examination. Instead of focusing solely on receiving signals from space, scientists are now sifting through archival spacecraft data with advanced tools such as quantum processors, AI-driven pattern recognition, and high-dimensional statistical analysis. Probes like Voyager, Pioneer, New Horizons, and even Mars orbiters are now being re-examined, not just for performance logs, but for what might have previously been dismissed as glitches or environmental noise. Under this new framework, every telemetry stream could be a potential signal. Each corrupted packet might contain meaningful information. This approach mirrors the early days of radio astronomy, when scientists puzzled over brief radio bursts or pulsars without knowing their origins. In the case of Voyager 1, It wasn't the message content that sparked debate, but the occurrence of non-random structure that persisted even after advanced analysis. SETI 2.0 proposes a radical idea. What if the signals we're looking for are encoded not for us but through us? If machines like Voyager act as inadvertent intermediaries, translating unknown interactions into structured data, then our technological creations might themselves be part of the very communication fabric we've been searching for. This doesn't require alien intent. All it needs is that structured information arises in ways our tools can detect, even if our current frameworks aren't equipped to interpret it. SETI 2.0 suggests that the distinction between signal and noise isn't fixed. It evolves as our technology advances. As our instruments grow more sensitive and our analytical methods become more sophisticated, we may begin to detect signals we never thought to search for, not in the stars but in the data already flowing from our machines. Voyager's longevity might be impressive, but the real surprise may lie in the data it carries, concealed in plain sight, and the way it has inspired a paradigm shift in how we understand the search for extraterrestrial intelligence.